Bismillahirrahmanirrahim. Today we'll talk about Kleene theorem. What is basically a Kleene theorem is, as per the Kleene theorem, any language that can be defined by a regular expression or finite automata or a transition graph, it can be defined by all three methods. So far, we have already discussed what is regular expression and how we can convert a descriptive form into the regular expression. And we have already discussed how the regular expression can be converted into finite automata and also into the transition graph. So all the three of these methods of defining the languages are basically equivalent. So this theorem is one of the most important and the fundamental results in the theory of finite automata or theory of computation. So these are basically three main things inside the theorem, that if we need to show that set of all finite automatas that can be defined by the set of transition graph. Show that the set of all the transition graphs are defined by the regular expression, and all the regular expressions can be defined by the finite automata. It means that finite automata can be converted into transition graphs can be converted into regular expression, and the regular expressions can ultimately be converted into finite automata. And all these three were basically representing the same language. Every finite automata is a transition graph by default, while every transition graph may or may not be a finite automata. Because in those transition graphs where we have more than one initial state, so that transition graphs will not be the finite automata. And also those transition graphs which consist of multiple symbols are also not the finite automata in a single transitions. Those finite transition graphs that contain an empty string or null move, empty or null move, they are also not the finite automata. So here are the three sections of the three parts of the Kleene theorem. The first part is, if a language can be accepted by a finite automata, then it can be accepted by a transition graph. Now let's do the proof one by one. Let's first start with the part one proof. For the part one, the Kleene theorem part one, every language that can be defined by a finite automata, it can also be defined by the transition graph. So for this, we don't need to do any sort of proof. Why? Because every finite automata is itself already a transition graph. So therefore, any language that can be defined by a finite automata has already been defined by the transition graph. Now, let's move to the Kleene theorem part two. If a language can be accepted by transition graphs, then it can be expressed by the regular expression, or a transition graph is then converted into the regular expression. So let's see this part. Every language that can be defined by a transition graph, okay, can also be defined by the regular expression. In order to prove that, we need to use some constructive algorithm that works how a regular expression can be obtained from a corresponding transition graph. For this purpose, the transition graph will be changed into generalized transition graph. We already talked about what are generalized transition graph. In that generalized transition graph, the labels of the transitions are basically the whole regular expression. Now let's start doing the proof. The proof of this part will be a constructive algorithm, as what we have discussed previously. This means that we present a procedure that starts with a finite automata, then the transition graph, and ultimately with a regular expression that basically defines the same language that was defined by the finite automata. Transition graph is basically an intermediate state where when we convert a finite automata to the regular expression. Because during the conversion, finite automata become a transition graph or a generalized transition graph, and then it will no more be a finite automata. As we have already discussed, that every finite automata is a transition graph, but every transition graph may or may not be the finite automata. For instance, we can, maybe in some cases, we can have more than one initial state, and a string can be used as a transition in the case of generalized transition graph. So instead of calling it finite automata, so we will call it as transition graph or a generalized transition graph. So let's do this steps one by one in order to convert the transition graph into regular expression or finite automata to the regular expression. Now, first of all, if you can see here, this is one of the example. In the step one, what we need to do is, if you have a transition graph which has more than one starting state, what you need to do is you need to introduce a new state that connect the new state with the old starting state by the transition, which is labeled as epsilon or null or empty, and make the old start states as a non-start state. So you can see here we have a diagram. Here we have one initial state, another initial state, and this is basically one transition graph. What we did here is we actually we make a new state as a starting state, connecting with those previous starting ones, and now these ones and one and two is no more a starting one, and we label it these transitions with empty. Here is also another example. You can see I have one, 3 and 5. There are 3 starting states. So what we did, we introduce a new starting one and we connect these with the empty one. Step 2 is, if the transition graph has more than one final state, what you need to do is you need to introduce a new final state that connect the new state to the old state. And the same thing is, now the old final states will no more be the final states. And it will be, those transitions will be labeled by epsilon. So previously 3 and 4, node 3, node 4, they were basically a final states. We include a new state, and here 3 and 4 is now no more the final one, and we empty it with the epsilon. Here also 9 and 12, they were the 2 final states. So what we did, we actually introduced a new state and we make that state as a final. Now these will be no more the final states, and we connect these two with the epsilon. Similarly, here you can see that we have Q0, Q1, and 3, it is Q3 and Q2 as a final state. So here we include a new state, which is basically Q4, and Q3 and Q2 will not be the final state, and here the transitions are labeled with epsilon. Now let's see step number 3. If the state has more than one incoming transition edges labeled by a corresponding regular expression from the same state, including the possibility of loop, then what we need to do is we need to replace all these transition edges with a single transition edge labeled by the sum. As you can see here, what you have 4 and 5. This one is incoming, this one is also incoming. It is exactly the same thing that we did previously. Is, for example, if we have a state Q0 and here we have a state Q1, okay, if you have a language which is A plus B, it indicates that if you have a language, okay, if someone has written a regular expression which is A plus B, what are the possible string? The possible string is either A or B. For this particular regular expression, if I need to make a finite automata, you can make it like this. You can write it as A comma B. You can also make it as Q0. This will be Q1. And in here, you can write A. In here, you can write B. The same thing can be represented as, you can write it as Q0. Here it will be Q1. And I can write here is as A plus B. All these 3 are basically representing the same thing. So same is the case here in this particular diagram. You can see one of the incoming is R1, another one is R2. So what we did, we wrote R1 plus R2. Now, in the state number 5, there are 2 incoming. One of the incoming is R3, another incoming is basically R4. So what we did, we wrote in putting just one incoming, and it will be R3 plus R4. It is exactly the same thing that we did, A plus B. Here you can see, here is basically a loop of R1, R2, and R3. What we did, we make it just one loop and we make R1 plus R2 plus R3. Now, if I need to write a regular expression for that, what I will do, I will write regular expression is equal to R1 plus R2 plus R3 whole star. Keep in mind, when the loop is still, yani this loop is still there, we are not allowed to write here the star. Okay, we will write static when we will yani not represent this particular loop. So that's why currently it will be just R1 plus R2 plus R3. But if I need to write a regular expression for this diagram, then in that case I will use this static. Similarly, this is same like the previous diagram. It will be R1 plus R2. Now let's move to the next state, next step. Bypass and state elimination. In this case, what we need to do is three states in a transition graph that are connected in a sequence. Then we need to do what? We need to do the elimination. Then eliminate the middle state and connect the first state with the third state by a single transition labeled by the regular expression, which is basically the concatenation of the two corresponding, yani corresponding to regular expression. We will see. Let's consider this particular diagram. Okay. In this case, you can see I have 1, 2, and 3. 2 is an intermediate. Let's remove this, connect 1 directly with 3. So here, what we have, we wrote it as R1, R1, R3. In this case, we have also 1, 2, and 3. We need to remove 2. So you can see here is that what we did, we have R1, then the loop of R2, and then R3. Here you have seen, I have completely removed this node. That's why here I wrote R1, R2 static, and then R3. In this case, I have not removed the, loop is still yani there. I just combine these three. That's why we wrote it as R1, R2, and R3. Let's consider this particular example. In this example, what we did, we have node 1, we have 2, 3, 1, 2, 4, 1, 2, 5. What I need to do is I need to remove this. So if while removing this, let's first see all the possible paths. One of the path is 1 to 2, 2 to 3. Another is 1 to 2, 2 to 4. Another is 1 to 2, 2 to 5. Now let's write the regular expressions for all the paths 1, 2, 2, and 3. So it will be R1, R2 steric, R3. Here it will be R1, R2 star, R4. Here it will be R1, R2 star, R5. 1, 2 star, 3. R1, R2 star, R4. R1, R2 star, and R5. So what we did here we have connected 1 directly with 3, 1 directly with 4, 1 directly with 5, and we replace this with those regular expressions. Now, let's consider this particular example. This is an important thing. Here you can see I have 3 states. One is Q0, another one is Q1, another one is Q2. Now, what I need to do is I need to remove Q1. In order to remove Q1, you see this diagram. Here we have Q0, here we have Q1 and Q2. We need to remove Q1. Now, in here, when we need to remove Q1, let's see the possible paths. We have a path which is from Q0. We have looked, one of the thing is from Q0 to Q1 and then again Q0. And there is another path which is from Q0, then Q1, and then Q2. So here what we did, if you can follow this path, so it will be A, this will be loop of B star, and this will be A. So you can see here Q0, we put a loop of A, B star, A. And there's also a path from Q0 to 1. So Q0 to Q1 and Q1 to Q2. So Q0 is to 1 is A, Then in Q1, there is a loop and then A. So that's why it is A, B star, A. If I need to finally convert it into the regular expression for this one, what will be basically the regular expression? The regular expression in this case will be equal to A, B star, A whole static, and then A, B star, A. So if someone want to write a regular expression, this is basically the regular expression. Now let's see another diagram. In this diagram, what I need to do is, let's assume here are only two states, and you can see there is an incoming, okay, from, it's a loop, yani Q0 to Q1, and then again from Q1 to Q0. So if I want to delete this one, what I will do, you can see this loop will be as it is. So you can see I will have how it will be, and we will be having here Q0, then we will be having a loop of B is as it is, then there will be another loop as well, and that will be A, then A star, and then A. So it will be A star, and then A. And then if we will combine these two, it will be Q0, and we will make it as a single loop. So B plus A star, A. And if we will write a regular expression, it will be B plus A steric, A whole steric, whole steric. Now, what we have done to the transition graph without changing the set of words it accepts, okay, we have eliminated one of the state. We have here eliminated Q1, here we have eliminated also Q1, here also we have eliminated this 2. We repeat this process again and again until we have eliminated all the state except the unique start and the unique final state. So let's consider this particular example. In this case, you can see you have a unique one initial state as well as the one final state. Now, what we need to do is we need to remove the nodes one by one. Let's first delete the node. For example, if you want to delete the node 2. So in order to delete this node, I need to first of all define all the paths. You can see here we have defined the paths. One of the path is from 1 to 2 and then 4. Another path is, so what we did, we have a path, okay, we have this path 1, 2, and then 4. We have another path 1, 2, and 5. And then from 3 to 4. And then 3, 2, and 5. So these are basically 4 paths. So from state 1 to state 4, 1 to, from 1 to 4, from 1 to 5, and from 3 to 4, and then from 3 to 5. So for each and every path, what we did, we wrote a regular expression. So for this one, you can see for this particular path from 1 to 2, it is AB. Then in 2, there is a loop of A. And then from 2 to 4, it is BA. Let's check from 3 to 5. From 3, it is BBB, 3 to 2. Okay, then in 2, it is A steric. And then 5 is B. So that's why here you can see in the same way we have these 1, 2, 3, and 4 regular expression, a part of regular expressions. So this was the original one. Here what we did, we extracted 4 regular expressions by deleting this 2, and ultimately from 1 to 4, you can see here there is a path from 1 to 4. Here is the equation that is written. Then from 1 to 5, so 1 to 5, this is the regular expression. From state 3 to 4, so this is from 3 to 4. This is the regular expression. and ultimately from 3 to 5 we have this. So it is basically, if you can see, it's all like all of them are incoming, yani they are basically, there are 2 incoming in 4 and 2 incoming in 5. So it will be initially, the same thing is, if there are 2 incoming, you can see if we have Q0, and in Q0 there are 2 incoming. One incoming is A, another incoming is B. So how we can write it? It will be like an A plus B. So same is the case here. So there are in 4, one of the incoming is this, another incoming is this. So it will be ABA steric BA plus triple B A star BA. Same is the case, yani for 5, there are 2 incoming. One of the incoming is this, another incoming is this. So we will take the sum of this one and this one. And ultimately, these 4 and 5 is incoming inside this. So it will be the sum of all these 4. So this is basically the regular expression. Let's consider this case. It's an important case. Yeah, this is one of the example, a part of the example. I have 1 2 3 as the state. Okay, if I need to remove 2, let's assume if you have removed 2, what you did, you have actually taken 1. For 1 there is a loop R1, R2 star and R3. So R1, R2 star and R3. And what I did, I also defined a path 3 to this R4 and 2. So I split this graph into 2 parts. Now, is this the correct way? No. Why it's not a correct way? Because we have a path from 3 to 1. But if we will see this diagram, there is no path from node 3 to node 1. So whenever you need to eliminate the state, you need to make sure that you have defined the path. You have not missed any path. So you have defined all the paths that is mentioned in the initial diagram. So that's why what happened, that there is also another path which is defined from 3 to 1, and which is basically R4, R2 steric, R3. This is basically R4, R2 steric, R3, because this is the path. This one, and this one. Let's consider this particular example. In this case, if I need to eliminate this, so let's see what are the possible paths. It will be Q0, Q2, Q3, Q0, Q2, Q4. It will be Q0, Q2, Q5. From Q0, all these 3. Now from Q1, I have to define the path. Q1, Q2, Q3, Q1, Q2, Q4, and Q1, Q2, and Q5. And here those regular expressions are basically written. Okay, so you can see here for Q0, Q2, Q3. So it will be R1, R3 star, and for Q3, R4. So in the same way, we need to define it for all those things. So if you can see here, how many we have? 1, 2, 3, 4, 5, 6. So it is 1, 2, 3, 4, 5, 6 paths. So whenever we remove an edge or a state, we must be sure that we have not destroyed any path through T that may previously have existed. Destroying a path will basically change the language. Since there are only finitely many paths in the whole transition graph, okay, we don't need to count, Yani, that, okay, if this is this time loop, you just represent it as a loop. We can check this possible in a finite number of steps. Let's consider another example. Let's consider this particular example. In this case, what we need to do is we need to eliminate this one. So if we need to eliminate this node, first of all, let's convert this into a part of regular expression. This one is not a finite automata. It is basically a transition graph. Why it's a transition graph? Because you can see we have two letters, more than one letters in a single transition. So what we will do first, you can see here, it will be AA plus BB. This will be A plus B. this, and so on. Okay, so what we did here, we just converted into this. Now the second thing is what we will do. Let's assume we want to eliminate 2. So 1 will be directly connected with this one having AA. Then maybe we will also, remove 3 and when you remove 3, you will actually having directly this B B. Okay, after this what will happen, I can replace these two with AA plus B B. Okay, so what you did in this case, you ultimately at the end you left with this thing that you will be having, yani here. Okay, what I will be AA plus BB, A plus B, and in this case, let's assume I will call this as 0, this one as 1. Okay, I remove, yani, this is 1, so I remove 2, so now I need to also remove 3. So it will be, yani, here 0, then it will be AA plus BB, then it will be 1, and on 1 there is a loop of A plus B, and then in here, okay, this final state I might call it as, for example, 4. Okay, so here will be basically 4, and it will be AA plus BB, and ultimately at the end I will convert this into a regular when I will remove, yani, this one. So it will be from 0 to 4, and 4 is also the final state. So here the expression, regular expression, will be AA plus BB, and here will be this, and then A plus B whole steric, because here is a loop, and then again here will be AA plus BB. So here is the final regular expression. You can do it like this, and also you can terminate it like what is given in these slides. Let's solve another example. We have a transition graph that accepts a string with an even number of A's and even number of B's. Here is the example. Let's solve it. So first of all, you can see the most important thing is that your initial state has also an incoming, and your final state also have the outgoing. If you have in the initial state there's an incoming, and in the final state it's an outgoing, what we need to do is you need to define a new state, okay, as an initial state, and that mark the transition as null move, and final, you can make a new state as a final and make null as a transition. And then what we need to do is here, if you have this diagram, let's first eliminate 2. When you eliminate the 2, so the path will be, because I need to eliminate 2, okay, on 1 there is one, this loop, okay, will not touch this loop, will only when eliminate 2, so it will be AB plus BA, then there is a loop of AA plus B, and then it will be AB plus BA. So the path from 1 to 2, okay, 1 becomes a loop at a, so it became a what? It became, here you can see there is a loop. And now it is same like that. Let's assume this is R1, this one is R2. So it will be R1 plus R2. So what we will do, so here what we did, that yani this thing will be equal to this plus here, this one. Okay, and ultimately at the end, I need to delete 1 as well. When you delete 1, so it will be, when you delete this node, so it will be exactly this thing, and here we just put a static. So this is the final regular expression. So this is all about, how we can, the second part of the Kleene theorem, that how we can convert a finite automata into the regular expression. So in order to convert the finite automata, first we convert it into the transition graph, and then convert the transition graph or a generalized transition graph into the regular expression. That's all about this part. Inshallah, in the next lesson, we will see what is basically the third part of the Kleene theorem.